Electric current is a continuous flow of charge through a wire. It is the rate of charge past a certain point. The greater the current, the more charge that passes that point. Current is measured in amperes, or amps for short. Think of it like a water hose. The water coming out of the nozzle is like current. A certain amount of water passes through the nozzle at a given moment. If more water is needed, then the flow is increased, and more water goes whooshing past the nozzle. The water is like current, and amps are used to measure how much of the current goes past a point in a given amount of time. The greater the current, the higher the amperage. There are two types of current. One is called alternating current, or AC for short. The other is direct current, or DC. Direct current is the kind of current we get from batteries. This kind of current always travels in the same direction. Alternating current is the kind used in homes, businesses, and schools. This kind of current is developed at a power plant. It is used because it is easier to send from the power plant to places that will use the electricity. It is called alternating current because it is produced when magnets spin in a coil of wire. Michael Faraday found out in 1831 that when a magnet moves in a coil of wire, an electric current is produced. If we look closely at the movement of the magnet and compare that with what is happening with the voltmeter needle, we see that when the magnet goes into the coil, the needle moves one way, and when the magnet is pulled out, the needle moves the other way. So as the magnet moves in the coil, the current alternates between two different directions. In the United States, the current alternates at the rate of 120 times per second for 60 complete cycles per second. For a flow of electricity to occur, we must have what is called a complete circuit. A circuit is made up of three parts: a source of electrons, a path for the electrons to travel along, and a device to use the electrons. We can make a simple circuit using these materials: a battery, some wire, and a flashlight bulb. The battery will provide a supply of electrons. The wire will form the path from the battery to the bulb and then back to the battery. When everything is connected, the bulb lights up. The current flows from the negative terminal of the battery through the wire to the bulb and then back to the positive pole of the battery. The path must be complete without any breaks or gaps. When there is a break in the circuit is said to be open, and the light goes out. When the circuit is closed and no gaps are present, the bulb lights. Switches are added to circuits to make it easier to open and close the circuit, and therefore control the flow of current. Current must always flow in a complete circle, from the source of electrons through the electrical device and back to the source of electrons. This is true for circuits in homes, schools, and businesses as well. Notice that the outlet has two vertical holes or slits and one smaller round hole. The round hole is for grounding electrical devices that you plug into the outlet. This way there will be less of a chance for electrical failures and damage done by short circuits. The two vertical slits are for the prongs of the electric cord of an appliance. The current flows along one prong and into the device, and then back out of the device and through the other prong into the other outlet slit. You may be wondering why the power cord prongs have holes in them. Well, inside the outlet are little ball clips that pop into these holes and help hold the prongs in the outlet. The wires are made of a good conductor which lose electrons from its atoms. For instance, atoms of copper have a weakly held electron in their outer electron shells. That means the electrons in orbit around the nucleus of copper atoms are loosely held and can be pushed out of orbit when a free electron comes near its orbit. Now that released electron can move to another copper atom and cause its outer electron to jump away. This is repeated over and over again as the current is flowing through the circuit. The push behind the current is called voltage, and is measured in volts. You have probably seen dry cells marked as 1.5 volts. If a flashlight bulb is rated as a 3-volt bulb, it would only dimly light if we connect the dry cell to it. But if we attach two 1.5 dry cell batteries together like this, we will increase the overall voltage to 3 volts, and the bulb lights brightly. The amount of electrical energy used in a certain amount of time is measured in what is called watts. Wattage is the measure of electrical use multiplied by time. So a 100-watt bulb burning for 10 hours uses 1,000 watts of energy. 1,000 watts is called 1 kilowatt. The power company keeps track of how much electrical energy a home or business is using by reading electric meters, which are often found outside a building. The main electrical wire from the power company goes to the electric meter, and then into the circuit box of the building. The electric meter has 5 dials, each with 10 numbers from 0 to 9 written on them. An arrow on each dial moves around as more and more electric current flows through the meter. See the disc spinning? That disc is recording the flow of current into this home. It will spin very fast if a lot of electrical devices are being used at the same time. If everything in the home that ran on electricity were to be turned off and unplugged, then the disc wouldn't move at all. The dials are read by someone from the power company, and the number is recorded. The next time the person from the power company reads the dials, a new number is recorded. The first reading is subtracted from the second reading, and a total for how many kilowatt hours of electricity have been used during that time period is established. The first dial on the far right is the ones column. The next dial is for the tens column, and so on until the last dial represents the 10,000s place. Electrical consumption is measured in kilowatt hours, so if the power company charges 10 cents per kilowatt hour, that 100-watt light bulb burning for 10 hours costs 10 cents. After the electric wires go into the electric meter, they go into the building's circuit box. This box then provides a series of separate circuits for the electric current to flow through. For instance, the clothes washer and dryer will probably need greater push to do the kind of electrical work they are designed to accomplish, so a special 240-volt circuit is set up for those electrical devices. Notice the plugs for the clothes washer is different from other plugs. Other circuits in the home will need typical 120-volt connections and outlets. So circuits are set up to run into different parts of the home to prevent one circuit from becoming overused. You see, the more electrical appliances that are plugged into a circuit and turned on, the greater the need for a greater flow of current. The more current that is flowing, the greater the danger of overloading the circuit and causing a fire. Circuit breakers are designed to allow a certain amount of amperage to build up in a circuit. For instance, a circuit may be designed for 20 amps. That means that as long as the amperage in that circuit stays below 20, the flow of current will continue. However, if the amperage goes above 20, then the circuit breaker trips and the flow of current is stopped. You may have experienced that when using a bunch of electrical devices at the same time. Suddenly, everything stops. That's an indication that the circuit has been overloaded and the amperage has risen above the circuit's limit. This is a safeguard because the wires in the circuit have been getting hotter and hotter, and if the circuit breaker didn't trip, a fire might have resulted. To correct the situation when everything shuts down, unplug some of the appliances and then reset the circuit breaker by flipping it back to the on position. Wattage is a measure of how much electrical energy a device needs to operate. Some devices have high wattage requirements, and some have very small needs. For instance, this 1200-watt hairdryer needs more energy than this 100-watt light bulb. The hairdryer uses a wire that resists the flow of electrons, and as a result glows red hot and gives off heat. Behind the wire is a motorized fan to blow the hot air towards your wet head. A lot of energy is needed to get the wires to give off all that heat and for the fan to operate properly. This light bulb also has a wire that resists the flow of electrons and turns bright as a result. However, the tungsten wire in the filament of the light doesn't need a lot of current, so its wattage is low. A 60-watt bulb isn't as bright as a 100-watt bulb. Amperage is the measure of current. To calculate amperage, you can divide the wattage of a device by the voltage that it requires. So the amperage for the 100-watt light bulb is less than 1. In a 20-amp circuit, we could have 20 100-watt light bulbs plugged in and on without tripping the circuit breaker. However, the hairdryer rated at 1200 watts will have an amperage of 10 amps. That means in a 20-amp circuit, we can't have other devices that use a lot of amps plugged in and turned on at the same time as we use the hairdryer. Otherwise, the circuit breaker may trip. You can find the wattage of most electrical devices on a special identification plate found on the back, side, or bottom of the appliance. Let's look at a few common appliances and compare their wattage. Remember, the higher the wattage, the greater the amperage. Things with higher amperage shouldn't be plugged in at the same time. Now it is time for the program quiz. The first 6 questions are multiple choice, and the final 4 questions are short answer. Question 1. Current is measured in what? A. Volts, B. Amperes, C. Electrons, D. Protons. Question 2. The push behind current is called what? A. Voltage, B. Amperes, C. Electrons, D. Wattage. Question 3. The amount of electrical energy used in a certain amount of time is called what? A. Voltage, B. Amperes, C. Electrons, D. Wattage. Question 4. Materials that allow the flow of electricity are called what? A. Insulators, B. Conductors, C. Wattage, D. Voltage. Question 5. A complete circuit is made up of what 3 things? A. Voltage, wattage, and amperes. B. Conductors, insulators, circuits. C. Source of electrons, a path, something to use the electrons. D. Electrons, protons, and neutrons. Question 6. 1,000 watts is called one what? A. Circuit, B. 120 volts, C. 60 cycles, D. Kilowatt. The next 4 questions are short answer. Question 1. How do circuit breakers protect our homes? Question 2. If a household appliance has a wattage of 720 and it uses standard 120 volts, what would the amperage be for this device? Question 3. Why is copper such a good conductor of electricity? Question 4. What does it mean when the circuit is open?